In this video, we're going to talk about periodic trends. Now, throughout this entire unit, we've talked about different types of trends and different types of patterns that we can see using the periodic table. Now, these patterns exist because of the periodic law. When the elements are arranged in order of increasing atomic number, they show a periodic repetition in their chemical and physical properties. 4 of the properties that we're going to talk about today is shielding effect, atomic radius, ionization energy, and electronegativity. Before we jump into these 4 different properties, we need to talk about the 2 things that affect these properties. Those 2 variables are distance and force of attraction. Now, we know that the nucleus that contains the protons is a positively charged nucleus, and we know that the electrons are negatively charged. Now, we talked previously that the electrons are attracted to the protons that are in the nucleus. So there is a force of attraction there. Now, when I talk about distance, I'm talking about the number of energy levels. Remember that each energy level represents the shells that you see here, or the rings that you see here. First energy level meaning 1 ring, second energy level meaning 2 rings, third energy level meaning 3 rings, and etc. and etc. So obviously the further out you go, the more distance there is, right? The more energy levels there are, the further the distance between the valence electrons and the protons in the nucleus. And then there's the force of attraction. Now we know that the electrons are attracted to the protons that are in the nucleus. And so if you think about it, if you have more protons in the nucleus, then you're getting a stronger positive charge, right? So if you're going from 1 proton to 2 protons to 4 protons, the attraction between your nucleus and the valence electrons is going to be stronger than the attraction between 1 proton and 1 valence electron. The first property we're going to talk about is shielding effect. Now think about the word shield. When do we use a shield? Or what do we use a shield for? We use a shield to protect, right? So the shielding effect is the decrease of attraction between the nucleus and the electrons because of the presence of energy shells. So remember that there is an attraction between the electrons that are negative and the nucleus that is positive because the protons are in the nucleus. Now, the more energy levels you have, or the more energy shells you have, think of that as an increase in the amount of shields between the nucleus and the valence electrons. Now, as you move from left to right across a period, shielding stays the same. And the reason why shielding stays the same from left to right is because you're on the same energy level. So if you take a look at period 2, lithium is on period 2 and neon is on period 2, and because they're on the same period, they're going to have the same amount of shielding in between their valence electrons and the nucleus. As we go down the group, shielding increases. So why does shielding increase? Because as you go down each energy level, what do you add? You add an energy shell. And the more shells you have, the more protection there is, right? So if I go to the 7th period, then imagine 7 rings, 1, 2, 3, 4, 5, 6, 7. And so there are lots of shields in between the valence electron and the nucleus, and it's shielding that attraction right here. Okay, so the more energy levels there are, then the more shielding there is. So let's take a look at some example problems. Which element has more shielding? Is it sodium or is it cesium? It's cesium. Why? Because cesium is further down the periodic table. Cesium is on the 6th energy level as opposed to sodium is on the 3rd energy level. Cesium has more shielding. Which element has more shielding? Carbon or oxygen? They're exactly the same, right? Because they're on the same period, they're going to have the same amount of shielding. The second property we're going to talk about is atomic radius. Atomic radius is the measure of the distance between the radii of two identical atoms of an element. So when I say atomic radius, it basically means the size of an atom, and the atomic size. Now moving left to right across a period, the atomic radius decreases. So it actually gets smaller as you move left to right. This is because of the force of attraction. As you go left to right, you're adding more protons. And so if you're adding more protons, that means the charge in your nucleus is getting stronger and stronger, right? It's getting more positive. And think about the electrons. The electrons are going to be on the same exact energy level. The electrons are not going further out, right? And so if the nucleus is getting stronger and the electrons are still on the same level, then the attraction between the nucleus and the electron is getting stronger, and the nucleus is tugging at those electrons a little bit more. So let me use period 2 as an example. So lithium has 3 protons, and then fluorine has 9 protons. Okay, so 3 protons versus 9 protons. You know that 9 protons will have a more positive charge, a stronger positive charge than the 3 protons in lithium. Now, if you take a look at the diagram that I drew for lithium and fluorine, we see that both of these are on the same exact level. It has 2 energy shells, right? And the difference here is that lithium has 1 electron on the 2nd energy level, and that fluorine has 7 electrons on the energy level. Now, as you increase the nuclear charge, so the nuclear charge gets more positive, right? Because it has more protons in a nucleus, it's tugging at these electrons more. So it's pulling those electrons in a little bit closer. And so as you go left to right, the size of the atom gets smaller and smaller and smaller. Now, moving down the group, the atomic radius increases. The size of the atom gets bigger. Why? Because of the additional energy levels, right? If we just draw the energy levels, we can see that as we go from the 1st energy level to the 4th energy level, that the size of the atom is getting bigger. Now, to help you remember this trend, think of a snowman. When you build a snowman, you have a small head, and it gets bigger and bigger as you build a snowman. So draw the snowman on your notes as well. And then imagine that the snowman fell over to the right, and always falls over to the right, and that indicates the atomic size getting smaller and smaller. And this is for every single column, every single group, and every single period. Now I'll show you how to use a snowman when we do practice problems like these. So which one has a bigger radius? Which one has a bigger size? Is it sodium or potassium? So let's find that first. Here's sodium and here's potassium. I'm going to draw the snowman, or imagine a snowman. And that tells you which one has the bigger atomic size. Potassium has the bigger size. What about sodium or magnesium? So let's find those elements. So here's sodium and magnesium. We're going to draw the snowman falling over because these elements are side by side. So which one is bigger? Sodium is bigger. Now this one says which one is smaller, phosphorus or chlorine. So here's phosphorus, here's chlorine. I'm going to draw the snowman so that it's touching those 2 elements there. So which one is smaller, phosphorus or chlorine? It's chlorine that's smaller. Now let's talk about size of ions. We're going to talk about cations and then we'll talk about anions. Remember that cations are positive ions that lose their electrons. So cations are smaller than their parent atom, than the normal neutral atom. Now if I draw lithium, a normal lithium looks like this. It has 3 electrons, 2 on the first ring and 1 on the second ring. Now, a lithium ion will lose that 1 valence electron, and when it loses that 1 valence electron, that goes away, and so does the outer energy level. And so what happened when the electron from the lithium went away? Because the outer shell also went away, you can see that clearly the size is smaller. So because of that loss of the outer shell, cations are smaller than their neutral atom. Now anions are larger than their neutral atoms. Here I drew nitrogen, and this will be the nitrogen ion where it gains 3 more electrons. Now what happens in the ion is that when it gains the 3 electrons for this example, think about what happens between the electrons themselves. Because electrons are negative, they repel each other, so they push each other away just a little bit. And when they push each other, they expand a little bit, and so the size gets bigger. So let's take a look at these practice problems. Which one is larger? Is it the sodium, neutral sodium, or is it the sodium ion? Remember that the cations are smaller than their neutral atom, and so the sodium, the neutral sodium, is larger. Which one is smaller between sulfur and the sulfur ion? Because the anion is larger than the neutral atom, in this case, the sulfur would be the smaller one. Now, in general, though, both cations and anions increase in size as you go down the group. Why? Because you're adding more of those energy shells, right? It's the same reason as before with atomic radius. And in general, cations and anions will decrease in size moving across the period because, again, of the increasing positive charge in the nucleus. So you can see that here in this picture, as you go down for the cations, the size is getting bigger. As you go down for the anions, the size is getting bigger. When you look at the ions in the same period, you can see that these are also just getting smaller as you go across a period. And for the anions, same thing. As you go across a period, the size is getting smaller. Next, let's talk about ionization energy. Ionization energy is the energy required to remove an electron from an atom. So when we're talking about removing an electron, we're really talking about removing that valence electron. Moving left to right across a period, ionization energy increases because of the increase in positive charge that is attracting the electrons to the nucleus, right? So when this says that ionization energy increases, it means that the higher the value, the stronger the hold on its valence electrons. It doesn't want to let those electrons go. It's going to take a lot of energy to strip the electron from the atom. Moving down the group, ionization energy decreases. Because think about it, if as the size gets bigger and the valence electron is further away from the nucleus, then first of all, the attraction is weaker, and it's easier to strip that valence electron away from that atom. So if you take a look at this picture, the attraction between the nucleus and its valence electron, if it's only about 2 levels away, is going to have a strong hold on that electron. And so it's going to take a lot of energy to strip that electron away from this atom. As opposed to this picture, where this attraction is weaker because the electron is further away from the nucleus. So it's not going to take that much energy to strip that electron away. So if you take a look at this chart, this shows you the different ionization energy values. You can see that the highest in group 1 is hydrogen. It has a high ionization energy value, meaning it doesn't want to let go of that electron, so it's going to take a lot of energy to strip that away. Whereas as you go down the group, you can see that the numbers are generally decreasing, and so it's much easier to strip that electron away from cesium than it would be from hydrogen. And as you go across the period, you see that the general trend is that the value is increasing. Remember what we talked about with noble gases? It doesn't want to let those electrons go, right? And so it will take a lot of energy in order to strip the valence electron away. So if you take a look, which one has the highest ionization energy value? It's helium. Helium really doesn't want to let go of those electrons. Now, just like how I taught you the trick to remember the snowman with atomic radius, to remember ionization energy, think of an ice cream cone. Ice cream, ionization energy. So for ice cream cone, biggest on top, and then as you go down the cone, it gets smaller and smaller. Let's say that the ice cream cone fell to the right, and it always falls to the right. So you start off small versus it getting bigger and bigger as you go to the right. So let's take a look at these examples. Which element has a higher ionization energy value, magnesium or calcium? So first find it. Here's magnesium, here's calcium. Let's draw an ice cream cone like that. So which one will have a higher ionization energy value? It will be magnesium. Which element has a higher ionization energy value? Is it aluminum or sulfur? So here is side by side. You can draw the ice cream cone. You can see that sulfur has the higher value. You can also think of it as, well, nonmetals in general will have the higher ionization energy value compared to its metals. Because remember, nonmetals tend to gain the electrons, as opposed to the metals, they will lose the electrons. Which element will have a higher ionization energy value, cesium or barium? So here, cesium and barium side by side. Draw the ice cream cone. You can see that barium has a higher ionization energy value. The last trend we'll look at is electronegativity. Electronegativity is the measure of attraction an atom has for electrons in a chemical bond. So in a chemical bond, the atom with the greater electronegativity value is more strongly attracted to the electrons in the bond. So think of a tug-of-war game. In a tug-of-war, imagine that it's me and you. Well, who wins the tug-of-war game? It's really the person who's stronger, right? And whoever can get the flag over to his or her side. So if you and I were in a tug-of-war game, the chances are you're probably stronger than I am, and you'll be able to pull the flag over to your side. So think of electronegativity like that. Imagine two atoms that are in a bond, and in a bond, they're pulling those electrons, they're tugging at those electrons, and so whichever one has the higher electronegativity value is technically the stronger one that holds on to the electrons. So moving left to right across a period, electronegativity increases because, again, of the same reason, the increasing positive charge. Moving down the group, electronegativity decreases because of the increasing size, and so there's less attraction from the nucleus to the valence electrons. So if you take a look at this chart, you can see that the values decrease as you go down, so you can actually draw the ice cream cone for this as well. And as you go across, the general trend is that it increases across, so you can draw the ice cream cone that fell over to the right. And if you take a look here, what's missing from here? What family is missing? It's the noble gases that are missing, right? Why are the noble gases not there? Well, because the noble gases, remember, have a full octet. They don't want to bond with anything They are good. They want to be left alone, so they don't have an electronegativity value. Because an electronegativity value is indicating two atoms sharing electrons in a bond. And noble gases don't want to share. Noble gases are good with 8 valence electrons. So let's take a look at these problems. Which element is more electronegative, fluorine or chlorine? So fluorine or chlorine, you can draw the ice cream cone because it'll be the same picture. You can see that fluorine will have a more electronegative value. Sodium or potassium, here's sodium, here's potassium. Again, draw the ice cream cone. Sodium has a higher value. And last one, tin or iodine. Tin is here, iodine is there. Let's draw the ice cream cone. Iodine will have the higher value. And that's it for periodic trends.